And now in this lecture we'll answer on two questions. In the first question we'll find out the length of line segment X that is equal to DE. In the second question we'll find out the area, the shaded area that is inside this quarter circle. So we start with the first question. In the drawing we have triangle ABC. Angle ABC equals to 30 degrees and angle ACB also equals to 30 degrees. And this angle DAE equals to 60 degrees. We also know that line segment BD, this line segment equals to 5 units. And we also know that line segment EC, this line segment equals to 4 units. And we want to find out the length of line segment DE that is equal to X. Okay, so first of all we focus on triangle ABC. And in triangle ABC, you know that those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So I'll write it down. So here angle ABC, this angle equals to this angle, that is actually angle ACB. And both angles, they are equal to 30 degrees. Okay, repeat again. In triangle ABC, angle ABC equals to angle ACB, and both angles, they are equal to 30 degrees. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of those equal angles in triangle ABC, there are equal sides. In front of this angle we have side AC, in front of this angle we have side AB, therefore according to the rule that I mentioned, side AB must be equal to side AC. Okay, so here side AB equals to side AC. Okay, so those two sides, they are equal to each other. Okay, and we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. But first of all, we define angle BAD, this angle as alpha, and we define angle EAC as beta. I repeat again that the sum of the angles in triangle ABC must be equal to 180 degrees. So we have here one angle that is equal to 30 degrees, this angle that is also equal to 30 degrees, this angle equals to alpha according to our definition, plus this angle that is equal to 60 degrees, plus this angle that is equal to beta according to our definition. In total, the sum of those actually three angles, they must be equal to 180 degrees in total. So here the sum of the angles in triangle ABC must be equal to 180 degrees. So here 30 degrees plus 30 degrees equals to 60 degrees, and 60 degrees plus 60 degrees equals to 180 degrees. So here 180 degrees plus alpha plus beta is equal to 180 degrees. So here we subtract 180 degrees from this equation, and we'll get that alpha plus beta equals to 180 degrees minus 120 degrees is 60 degrees. So we found out that alpha plus beta equals to 60 degrees. In the next step, we'll do a construction. From point A, from the vertex A, we'll draw a straight line in such a way that the angle between side AC and the straight line will be equal to alpha. Okay, so we'll draw the straight line in such a way that the angle between side CA and the straight line that we will draw will be equal to alpha. So here this angle equals to alpha according to our construction. In the next step, from point C, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal to 30 degrees. I repeat again. This angle equals to 30 degrees according to our construction. Then we will extend the straight line from point C, and we will extend the straight line from point A until they intersect with each other. And we will define the intersection point between the extended straight line from A and the extended straight line from C as point F. Point F is the intersection point of the straight line from point A and the straight line from point C. So here we created triangle AFC. In the next step, we will prove the new triangle that we created, triangle AFC, congruent to triangle ABD. So I'll repeat again. We will prove the triangle ABD, this triangle, is congruent to this triangle, triangle AFC, that we created. So why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. This angle equals to alpha according to our construction, and this angle equals to alpha according to our definition. So I can write it down here that angle BAD, this angle, equals to this angle, that is actually angle CAF, and both angles are equal to alpha, therefore they are equal to each other. I repeat again. Angle BAD equals to angle CAF, and both angles are equal to alpha, therefore they are equal to each other. In addition, we have already proved that those two sides are equal to each other. So here, side AB of triangle ABD is equal to side AC of triangle AFC. Okay, side AB equals to side AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here, angle ABD, this angle equals to this angle that is actually angle ACF, and both angles are equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ACF, and they are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that triangle BAD, this triangle, congruent, this is the sign of congruent, to triangle AFC, and they congruent to each other according to angle side angle rule. So those two triangles can go into each other according to angle side angle rule. I repeat again. Those two angles and the side, that is to say alpha and 30 degrees, and the side that is attached to those two angles, that is to say side AB, correspondingly congruent to those two angles, and the side that's attached to those two angles, that is side AC. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we will conclude is that side BD equals to side FC. Side BD equals to side FC. Those two sides, the side BD equals to side FC according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding angles must be equal to each other. Okay? But according to what is given us in the question, side BD equals to 5 units. So I can write here that BD equals to 5 units. And from this equation, 5 equals to BD equals to FC. We'll conclude that side FC is also equals to 5 units. Okay, here, side FC is also equals to 5 units. In addition, the second thing that we'll conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. AD equals to AF. AD equals to AF. Again, AD equals to AF according to the same rule that corresponding sides in congruent triangles are equal to each other. So we'll define side AD as A. Here, side AD equals to A according to our definition. And from this equation, A equals to AD equals to AF, we'll conclude that side AF will be also equal to A. Side AF equals to A. Here side AF equals to A. Okay. In the next step, we will join points E and F together by a straight line. By joining points E and F by straight line, we created triangle EAF, and we prove that this triangle is congruent to triangle ADE. So we actually proved that the green triangle ADE is congruent to the orange triangle AEF. We'll prove that the green triangle is congruent to the orange triangle. But before that, we have already found out that alpha plus beta equals to 60 degrees. And here we have angle EAF equals to alpha plus beta, therefore it is equal to 60 degrees. This angle equals to 60 degrees. Now we'll prove that the green triangle is congruent to the orange triangle. So I'll write it down. We'll prove that the green triangle, that is actually triangle ADE, is congruent to the orange triangle, that is actually triangle AEF. So why those two triangles congruent to each other? First of all, we just right now proved that those two sides, they are equal to each other, they are both equal to A, therefore they are equal to each other. Actually, they are equal to each other because of the fact that the previous triangles, those two triangles congruent to each other, therefore those two sides are also equal to each other. So here, you can write down that side AD is equal to this side, that is side AE. Both sides are equal to A, therefore they are equal to each other. Okay, AD equals to AE equals to A. In addition, those two angles are both equal to 60 degrees, therefore they are equal to each other. So here, angle DAE, this angle, is equal to this angle, that is actually angle EAF, and they are both equal to 60 degrees, therefore they are equal to each other. I'll repeat again. Angle DAE equals to angle EAF, and they are both equal to 60 degrees, therefore they are equal to each other. And finally, this side is a common side. Side AE is a common side that belongs to both triangles, so this side equals to itself. So AE equals to AE is a common side that belongs to both triangles. Repeat again. Side AE equals to side AE is a common side that belongs to both triangles. So we actually proved the triangle ADE, the green triangle, is congruent. This is the sign of congruent to triangle AEF, the orange triangle, according to side angle side rule. I'll repeat again. Those two triangles can go into each other according to side angle side rule. Actually, those two sides and the angle between them in the green triangle can go in correspondingly to those two sides and the angle between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we conclude that side DE equals to side EF. Repeat again, from the fact that the green triangle can go into the orange triangle, we conclude that side D equals to side EF according to the rule that corresponding sides and congruent triangles are equal to each other. But according to what is given as the question, side DE equals to X. So can I tell that side DE equals to X? And from this equation, X equals to DE equals to EF, we derive that side EF is also equals to X. Side EF is also equals to X, so can I tell that side EF equals to X? In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle EFC. Okay, what is the law of cosines? Actually, the law of cosines is true in any triangle. So I told you that in any triangle, if we have triangle ABC that could be any triangle, this is triangle ABC. And we actually know that side AB equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta, and side BC equals to C units in its length. Then in this triangle ABC, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again, in this triangle ABC that could be any triangle, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement the law of cosines in triangle EFC. Okay, so I copy triangle EFC in this page and we'll implement the law of cosines in this triangle EFC. angle ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. Side FC equals to 5 units, according to what we have already found out. Side EC equals to 4 units, according to what is given us the question, and we just right now found out that side EF equals to X. So, this is triangle EFC that I copied from the original drawing. This triangle EFC, according to the law of cosines, write it down, according to the law of cosines, if we implement the law of cosines in this triangle EFC, we will get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I repeat again. We implemented the law of cosines in this triangle EFC. According to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here we found out that x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and we have to multiply minus 40 by cosine 60 degrees, but cosine 60 degrees equals to 1/2. So we substitute cosine 60 degrees by 1/2, and we get that x squared equals to 16 plus 25 is 41 minus minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21. So here we take a root out of this equation, and we get that x equals to the square root of 21. But because of the fact that x is a length, it must be a positive number, therefore we will have to take only the positive root of 21. And in terms of numbers, it will be equal to 4.58 units. I repeat again, the answer to the question is that the length of this 9 segment DE that is equal to x, it is equal to either the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. Okay, so we finished with the first question. In the next step, I will present to you the second question. So in the drawing we have a quarter circle. Inside this quarter circle, we have a circle and a semicircle that are tangent to each other at this point, and we also know that this circle is tangent to the semicircle at this point. And our mission is to find out the value of the shaded area. Okay, so first of all, because of the fact that this is a quarter circle, it means that this point is the center of the semicircle, so we define the center of the semicircle as point O, and write it down that point O is the center of the quarter circle, and this angle must be equal to 90 degrees. So this is a right angle. It is true in any quarter circle. And we'll define this point as point B, and define this point as point M. So here we have tangent OB is tangent to this circle as point M. Point M is the point of tendency. Point of tendency of tangent OB with this circle. I repeat again. Point M is the point of tendency of tangent OB with this circle. We define the center of this circle as point P. Point P is the center of this circle. Point M is the point on the circle itself, so PM is the radius of this circle that is equal to 2 units. Okay? So we have here the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MP. That is to say, this angle will be equal to 90 degrees, this angle will be also equal to 90 degrees, according to the rule that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, in this drawing, the radius OM, it is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay? And here also, we have the radius PM that is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent OB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OB will be perpendicular to the radius MP. So if OB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule number 1. Okay, so in the next step, from the center point P, we draw perpendicular on this straight line. So we define the center of the semicircle as point N. So actually here from point P we draw perpendicular on NO. So here this angle equals to 90 degrees according to our construction, and this angle also equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point E and NO as L. Okay? So actually we created here quadrilateral LPOM. Inside quadrilateral LPOM we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees. So in quadrilateral LPOM we have 3 right angles that the sum of them is 270 degrees, plus the size of the fourth angle that is actual angle LPM, this angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So here we subtract 270 degrees from this equation, and we get that the missing angle LPM, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that the missing angle, it is a right angle. So this angle equals to 90 degrees. So we actually found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral LPOM as a rectangle. So here, quadrilateral LPOM is a rectangle. Okay? Because all of its angles are right angles. Okay? And we also note that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of a rectangle LPOM are equal to each other. So, therefore, here PM must be equal to LO. PM must be equal to LO according to the rule that the opposite sides of a rectangle are equal to each other. But PM equals to 2 units. This is the radius of the circle. So from this equation 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that LP equals to OM. LP equals to OM. So if we define OM as X, so here LP equals to OM and OM equals to X according to our definition. So from this equation LP equals to OM equals to X, we'll derive that LP is also equals to X. So here LP is also equals to X. Okay, so here, according to what we can see in the drawing, this circle is tangent to the quarter circle at this point. That is to say, those two circular shapes have an internal notch between them, so we define the touching point of the circle and the quarter circle as point K. So I repeat again that those two circular shapes have an internal notch between them at point K. And whenever we have an internal notch between two circular shapes, it means that the straight line that connects their centers together must pass for the point of tendency, that is to say, it must pass for point K. So here in our drawing, we know that the center of the quarter circle is point O, the center of the circle is point P, and the straight line that connects the two centers together will be OP. And according to the rule that I mentioned, the straight line OP must pass for point K. That is to say, OPK is one straight line. Okay, so here, OPK is one straight line. The 3 points OP and K, they are all on the same straight line. Okay? Points O, P, and K, they are all located on the same straight line. Or in other words, we can write down that OPK is a straight line. So, if OPK is a straight line, OK must be also a straight line. So, you can conclude from it that OK is also a straight line. Here, point O is the center of the quarter circle. Point K is the point on the quarter circle itself. And this is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle. So we can write down that OK, segment line OK, that is actually a straight line, is the radius of the quarter circle. So we define the radius of the quarter circle as capital R, therefore OK equals to capital R. According to our definition, OK, that is the radius of the quarter circle, equals to capital R. So I write it down here also, that OK, that is the radius of the quarter circle, it is equal to capital R according to our definition. Point P is the center of the circle. Point K is the point on the circle itself. So PK is the radius of the circle that is equal to 2 units according to what is given as the question. So we can write down that PK equals to 2 and OK equals to capital R. And what is the value of OP, it is very easy to see from drawing that OP equals to OK minus PK. Again, OK minus PK equals to OP. So you can write down that OP equals to OK minus PK. Okay, so OP equals to OK minus PK. So we found out actually that OP equals to OK. OK is the radius of the quarter circle that is equal to capital R, minus PK is the radius of the circle that is equal to 2. So in conclusion, we found out that line segment OP equals to capital R minus 2. So we can write here that line segment OP equals to capital R minus 2. Now we can implement the Pythagoras theorem on the right triangle OPM. So I will copy the right triangle OPM in this page and we'll implement the Pythagoras theorem on this triangle OPM. Okay. The hypotenuse OP equals to capital R minus 2. OM equals to X. And PM equals to 2. This is the radius of the circle. So this is the right triangle OPM, and here by PT is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle OPM, the hypotenuse is OP, so the square of the hypotenuse is OP squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to PM squared plus OM squared. So OP equals to R minus 2, so OP squared is R minus 2 squared. That is equal to PM squared. PM equals to 2, so PM squared is 2 squared, that is 4, plus OM squared. OM equals to X, so OM squared is X squared. So in conclusion, we found out that according to equation number 1, R minus 2 squared equals to 4 plus X squared. So here we will open the brackets on this side of equation number 1 and we'll get that R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2 is minus 4R, and it is equals to 4 plus X squared. Here we have 4 on both sides of the equation, so 4 will get cancelled. So what is left from equation number 1 after we cancelled 4? What is left is actually we found out that X squared equals to R squared minus 4R. Okay. So in the next step, we'll focus on the touching point of the circle with the semicircle, this point. Here, those two circular shapes have an external knot between them at this point. Okay, so we define the touching point of the semicircle and the circle is point H. And we also have another rule that whenever you have an external notch between two circular shapes, like in this drawing, though the circle and the semicircle have an external notch between them at point H, then the straight line that connects their centers together, that is to say, here the center of the circle is at point P and the center of the semicircle is at point N, and the straight line that connects the two centers together is Pn. So this straight line Pn, must pass through the touching point of the two circular shapes. In this case, it must pass through point H. That is to say, here we get that PHN is one straight line. Okay? PHN is one straight line. According to the rule that I mentioned, line segment PHN is one straight line, and or in other words, you can see also, you can say also that the 3 points P, H and N are located on the same straight line. It is the same thing to say that P, H, N is one straight line, or the 3 points P, H, N are located on the same straight line. Okay, so if P, H, N is a straight line, then Pn is a straight line. Pn is a straight line. So here we created the right triangle PNPL. But so here point P is the center of the circle, point H is the point of the circle itself. So PH is the radius of the circle that is equal to 2 units according to what is given as the question. Likewise, point N is the center of the semicircle, point H is the point of the semicircle itself. Therefore, NH is the radius of this semicircle that is equal to 2 units according to what is given as the question. So in conclusion, the straight line NP equals to NH plus HP. The straight line NP equals to NH plus HP. Okay. So NP equals to NH, that is 2, plus HP, that is also 2. 2 plus 2 is 4, so we found out that NP, the straight line NP, equals to 4 units. We define this point as point Y. So point N is the center of the semicircle. Point Y is the point on the semicircle itself. Therefore, NY is the radius of the semicircle that is equal to 2 units. And what is the length of line segment NL. The length of line segment NL, it is very easy to see from the drawing that NL equals to YO, that is the radius of the quarter circle, minus NY, that is the radius of the semicircle, minus LO. I'll repeat again, the length of line segment NL equals to YO, that is the radius of the quarter circle, minus NY, that is the radius of the semicircle, minus LO, that is equal to 2 units. So line segment NL equals to YO is the radius of the quarter circle, that is equal to capital R, minus NY equals to 2 units, minus LO, that is also equals to 2 units. So NL equals to capital R, minus 2 is minus 4. So in conclusion, we found out that the length of line segment NL, it is equal to capital R minus 4. Okay. So now we'll implement the Pythagoras theorem on the right triangle, triangle NLP. This angle equals to 90 degrees according to our construction. From point P we draw perpendicular on NO, therefore this angle equals to 90 degrees. So I copy the right triangle NLP in a new page and we implement the Pythagoras theorem on this triangle, triangle NLP. We have already found out, we just right now found out that line segment NL equals to capital R minus 4, LP equals to X, this angle equals to 90 degrees according to our construction, and the hypotenuse NP equals to 2 plus 2, that is 4. Now we will implement the Pythagoras theorem on this right triangle, triangle NLP. So by PT is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is NP, so the square of the hypotenuse is NP squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to NL squared plus LP squared. NP equals to 4, so NP squared is 4 squared, that is 16. Equals to NL squared. NL equals to capital R minus 4, so NL squared is capital R minus 4 squared, plus LP squared. LP equals to X, so LP squared is X squared. So according to equation number 1, we found out that, according to equation number 2, we found out that 16 equals to capital R minus 4 squared plus X squared. Okay. So here 16 equals to, we open the brackets on this side of equation number 2 and we get that R minus 4 squared equals to R squared plus 4 squared, that is 16, minus 2 times R times 4 is minus 8R plus X squared. Here we have 16 on both sides of the equation, so 16 will get cancelled. What is left from equation number 2 after we cancel 16? In this side of the equation, nothing is left, so it is 0. That is equal to r squared minus 8r plus x squared. So here we'll add 8r to this equation number 2, and we get that according to equation number 2, 8r equals to r squared plus x squared. So here we subtract r squared from this equation number 2, and we get that according to equation number 2, 8r minus r squared equals to x squared. So we actually have two expressions for x squared. I write them together side by side in the new page. So actually, according to the first equation, we found out that x squared equals to r squared minus 4r. This is according to equation number 1, while according to equation number 2, we found out that x squared equals to eight r minus r squared. In the next step, I create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. X squared according to equation number 1 must be equal to x squared according to equation number 2. So x squared according to equation number 1 is r squared minus 4r, while x squared according to equation number 2 is 8r minus r squared. So here we add r squared from this equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. Okay, so here we will add 4r to this equation number 3, and we will get that according to equation number 3, two r squared equals to 8r plus 4r is 12r. So here we divide by 2 equation number 3, and we get that according to equation number 3, 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtract 6r from this equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we take a common factor of r from this equation number 3, and we get here, so we took from r squared, what is left from r squared after we took from it r as a common factor, what is left is r. And what is left from minus 6r after we took from it r as a common factor, what is left, it is actually minus 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we have two solutions that are possible for R. The first solution for R is that R equals to 0. But because of the fact that R is the radius of this quarter circle, it can never be equal to 0, it must be a positive number. So this solution is the correct solution, we cancel this solution, and we left only with the second solution. That R minus 6 equals to 0. Here we add 6 to this equation and we get that R equals to 6. So we found out that the radius of this quarter circle equals to 6 units. And what is the value of the shaded area? The value of the shaded area, equals to the area of the quarter circle is equal to the area of the quarter circle minus the area of the circle, okay, minus the area of the semicircle. It is very easy to see from the drawing that if we subtract from the area of the quarter circle the area of the circle and the area of the semicircle, it will give us exactly the value of the shaded area. I'll repeat again, that the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Okay? So the shaded area will be equal to the area of the quarter circle, and we know that the area of any quarter circle equals to the area of the circle over 4. And the area of the circle equals to pi r square, of course. R is the radius of the quarter circle, and pi r square is the area of the circle over 4 will give us the area of the quarter circle, the area of this quarter circle, and then we subtract the area of the circle. We know that the radius of the circle is 2, so the area will be pi r square, and r equals to 2, so it is pi 2 square minus the area of the semicircle. The area of the semicircle equals to the area of the circle over 2, and we know that r equals to 2, so the area of the circle is pi 2 square, and therefore the area of the semicircle will be equal to pi 2 square over 2. Okay, so we actually found out that the shaded area equals to the area of the semicircle equals to pi r square over 2, r equals to 6, so 6 square is 36, so it is 36 pi over 4 in total. This is the area of the quarter circle minus the area of the circle, that is pi 2 square. 2 square is 4, and 4 times pi is 4 pi, so in total the area of the circle is 4 pi square units minus the area of the semicircle. Because of the fact that they have exactly the same area, the circle and the semicircle, therefore the area of the semicircle must be equal to half of the area of the circle itself. So here we can see that 2 square is 4, and 4 times pi is 4 pi, and 4 pi over 2 is 2 pi. So the area of the semicircle is 2 pi. And here 36 over 4 is 9, and 9 times pi is 9 pi. So it is 9 pi, that is the area of the quarter circle, minus 4 pi, minus 2 pi. 9 minus 4 is 5, and 5 minus 2 is 3. So in conclusion, we found out that the area, the shaded area, equals to 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, here the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. We finished with the second method. In the next step, I will summarize the lecture. We start with the first question. So in the drawing we have triangle ABC. This is triangle ABC. Note that those two angles are equal to 30 degrees. Angle BAC equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And we want to find out the value of line segment DE that is equal to X according to what is given us in the question. So first of all, because of the fact that in triangle ABC those two angles are equal to each other, and we know that in front of equal angles in the triangle there are equal sides, it means that AB must be equal to AC. I'm repeating again. Because of the fact that angle ABC equals to angle ACB and both are equal to 30 degrees, therefore in front of those two equal angles there are equal sides. That is to say AB equals to AC. And then we define angle BAD as alpha, we define angle EAC as beta, and we know that the sum of the angles in any triangle, and especially in triangle ABC, equals to 180 degrees. That is to say 30 degrees plus 30 degrees, that is those two angles, plus this angle that is alpha, plus this angle that is 60 degrees, plus this angle that is theta. In total, the sum of those three angles in triangle ABC must be equal to 180 degrees. Here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in conclusion, we found out that 120 degrees plus alpha plus beta equals to 180 degrees. Here we subtracted 120 degrees from this equation, and we found out that alpha plus beta equals to 60 degrees, because 180 degrees minus 120 degrees equals to 60 degrees. So in conclusion, we found out that alpha plus beta equals to 60 degrees. Then we did a construction. From point A, we drew a straight line in such a way that the angle between side CA and the straight line that we drew, this angle will be equal to alpha. Again, angle CAF equals to alpha according to our construction. In addition, from point C, we draw a straight line in such a way that the angle between side AC and side CF will be equal to 30 degrees. So I repeat again that this angle that is equal to alpha and this angle that is equal to 30 degrees, they are both equal to alpha and 30 degrees according to our construction. Then we extended side CF and side AF until they intersect with each other, and we extended the straight lines from point C, and we extended the straight line from point A until they intersect with each other, and we defined the intersection point of the two straight lines that we drew as point F. And then we proved that those two triangles, that is to say triangle AFC and triangle ABD, can go into each other. So why those two triangles can go into each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. Okay? Angle ABC equals to angle AC, angle BAD equals to angle CAF, and they're both equal to alpha, therefore they're equal to each other. In addition, we have already proved that side AB equals to side AC. Side AB equals to side AC. Okay, AB equals to AC, and finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here, angle ABD equals to angle ACE equals to 30 degrees. Okay, so we actually proved that those two triangles can go into each other according to angle side angle rule. Why? Because we have those two angles and the side that attached to those two angles in triangle ABD are equal to those two angles, and the side that attached to those two angles, that is to say side AC, in the right triangle, triangle AFC. Therefore, we proved that those two triangles can go into each other according to angle side angle rule. Okay, I'll repeat again. Triangle triangle BAD can go into triangle AFC according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing, that we conclude that side BD equals to side AF. Side BD equals to side FC. Here, side BD equals to side FC according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be equal to each other. So BD equals to FC. But according to what is given us the question, BD equals to 5 units. Here BD equals to 5 units. And from this equation 5 equals to BD equals to FC, we derive that FC also equals to 5 units. Here FC also equals to 5 units. Okay? And the second thing that we derive from the fact that those two triangles can go into each other, that side AD equals to side AF. Again, AD equals to AF. According to the sum rule, that corresponding sides in congruent triangles are equal to each other. But here, if we define side AD as A, then here AD equals to A, and from this equation A equals to AD equals to AF, we derive that AF also equals to A. Here AF equals to also to A. In the next step, we join points E and F together by a straight line, and we proved that the green triangle is congruent to the orange triangle. Okay? So why those two triangles can go into each other? First of all, we just right now proved that AD equals to AE equals to A. AD equals to AE equals to A. In addition, those two angles, they are equal to 60 degrees. Why? Because we already found out that alpha plus beta equals to 60 degrees. So those two angles are both equal to 60 degrees, therefore they are equal to each other. So angle DAF in the green triangle equals to angle EAF in the orange triangle, they are both equal to 60 degrees, therefore they are equal to each other. And finally we have side AE, that is a common side that belongs to both triangles. So A equals to AE is a common side that belongs to both triangles. So we actually proved that those two triangles can go into each other according to side angle side rule. Actually, those two sides and the angle between them in the green triangle can go into those two sides and the angle between them in the orange triangle. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other according to side angle side rule, we conclude that side DE equals to side EF. Here, side DE equals to side EF. DE equals to EF. According to the sum rule, D equals to EF according to the sum rule that corresponding angles in congruent triangles are equal to each other. But here, side, according to what is given us the question, side D equals to x. So we can write here that D equals to x. And from this equation, x equals to D equals to EF, we derive that side EF also equals to x. Here, side EF is also equals to x. Okay? In the next step, I presented to you the law of cosines, and we implemented the law of cosines in triangle EFC. The law of cosines is true in any triangle. That is the reason that we can implement it in triangle EFC. So according to the law of cosines, in any triangle, if we have triangle ABC that could be any triangle, we know that side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. Then C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. The angle between side AB and side AC is theta. So C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Then we implemented it on the right triangle, triangle EFC. This is the right triangle, triangle EFC that I copied from the original drawing. And according to the law of cosines, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Here, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. So here, x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. So it is minus 40 times cosine 60 degrees is 1/2. So in conclusion, this expression equals in total to minus 40 times 1/2. So here we have x squared equals to 16 plus 25 is 41, and 41 minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. 41 minus 20 is 21, so in conclusion we found out that x squared equals to 21. Here we took a root out of this equation and we found out that x equals to either the square root of 21 or 4.58 units in terms of numbers. And actually x must be equal to the positive root of 21, positive square root of 21, because of the fact that x is a length and a length x is a length, and a length must be a positive number. So repeat again that the size of line segment x, the length of line segment x, that is equal to DE also. Either it will be equal to the positive root of square root of 21, or in terms of numbers, we can express it as 4.58 units. Okay, thank you very much.